Hello, everyone. We are researchers from Rensselaer Polytechnic Institute and IBM Thomas J. Watson Research Center. And today I'm going to introduce our work, Quantized higher order tensor recovery by exploring low-dimensional structures. Practical data sets may contain additional correlations that cannot be captured by low-rank matrices. For instance, if every frame of a video is vectorized so that the video is represented by a matrix, the spatial correlation is not directly characterized by low-rank matrices. And another example is the recommender system. Users' ratings against objects vary under different contexts. And here we provide an example. People might give ratings in good mode and bad mode. In this case, assuming the rating matrix is low rank does not fully characterize the dependence of ratings over the context. This motivates the usage of low rank tensors, where higher order tensors contain data arrays with at least 3 dimensions. And low rank tensors with quantization noise exist in hyperstructure data, rating systems, and many other applications. For example, many recommender systems ratings from users are highly quantized, such as like or dislike, and this is a binary case. And also there are many missing entries. For example, users do not give rating for all subjects, while the underlying systems may want to recover real-valued user ratings. In this work, we apply quantized tensor recovery method to reach such goal. Existing works on low-rank tensor recovery mainly consider random noise or sparse noise, where only a few works consider tensor recovery from 1-bit measurements. That is, all measurements are binary. We, for the first time, study low-rank tensor recovery from multi-level quantized measurements. But even for the binary case, the existing works only consider unfolding tensors to matrices or some convex relaxations. It turns out that the problem is not the same one, and the optimal solution of the new problem is worse than the optimal solution of the original problem. In this work, we solve the exactly non-convex problem and guarantee the state-of-art theoretical results. We also empirically extend to scenarios of unknown quantization rule and propose efficient algorithms with convergence guarantee. Here, we first give the definition of tensor ranks, where we introduce 2 ranks. The first one is CP rank. The curly QX is a W-order tensor. It can be decomposed into the outer products of W matrices, A1 to AW. Each matrix AK has ambient dimension NK, and they all have the same column number R. The smallest R one can find is the CP rank of the tensor X. Some tensors may have a special property and can be decomposed in the form of equation 2. This is a special case of CP rank. Zeta1 to zeta R are positive real values. V1 to VW are similar to A1 to AW, but are unitary matrices. We will call this tensor singular value decomposition as TSVD, and tensors have this decomposition as SVD tensor. We remark that not all tensors have such decomposition property, and we will prove that once the tensor have TSVD, then we could guarantee a better theoretical recovery error bound. And here we briefly introduce the problem we're going to solve. The W-order tensor X star contains ground truth data. And we also have a W-order tensor N, which is a noise, which contains noises, and our noises entries of this tensor are IID generated from a fixed distribution. And we assume we know this distribution, and the cumulative distribution function is phi. And Q is the quantization operator. It can map any x between omega L minus 1 to omega L to value L. And here's a simple example. This is a 3-order tensor, and Q will map the value to 1 out of k levels. So Y here is quantized tensors, and the tensor contains data, concrete data from 1 to k. And one can check that the entries of Y equals to L with probably FL, and this FL from L to from L equals to 1 to capital K and sum to 1. And then we can represent the probability of an entry of Y equals to L given the ground truth using the boundary pair and the CDF of the noise. The problem we're going to solve is, given the quantized observation Y, the distribution phi of the injected noise, can we recover the actual data X star? So for general tensor recovery, we will solve the following objective function subject to a feasible site. Since we already know the probability of Y equal to L given X, we can maximize the log likelihood function. And this is the same as minimizing the negative log likelihood function. And here the indicator function equals to 1 when the entry of Y equal to L. And K is the level of quantization. Omega is the observation site because we assume there are missing data here. And here we also assume that we do not know the quantization boundary. That is, quantization boundaries omega 1 to omega K minus 1 are unknown. But we set omega 0 equals to negative infinity and omega K equals to positive infinity. The feasible set includes the constraints we have. We assume the tensor X is a low rank matrix and the rank X is smaller or equals to R. And we also assume that the infinity norm of X is bounded by alpha. The quantization boundaries omega 0 to omega K obey the ascending order. For SVD tensors, the objective function is same to general tensors. The only difference is that there's an additional constraint because the tensor can be because the tensor satisfies the singular value decomposition. So we have additional constraint X belonging to ST-SVD. We also provide the theoretical results for recovery error. In our theoretical analysis, we assume that the quantization rule is known and there are no missing entries. We show that for general tensor, the upper bound of the recovery error is square root of R to W minus 1 times W log W over N to W minus 1. So if we assume that the order of tensor is a constant, then we can ignore the W in numerator. And for SVD tensor, the upper bound can be further reduced to square root of R over square root of N to W minus 1. And one can see that this is better than the general tensor case. We also provide a lower bound, which is a fundamental limit for any algorithms. We prove that for any algorithm, there will always exist some tensors with probability at least 3 over 4. The recovery error will larger than the order of square root of R over square root of N to W minus 1. And if the tensor satisfies low rank property, for example, the rank is constant, then one can see the upper bound and lower bound will have the same order, and this is order-wise optimal. We remark here that the theoretical results are built on the optimal solution. The bottom table shows a comparison among different quantized recovery methods. One can see that the 1-bit tensor recovery has a quarter power there because they use the convex relaxation. And all recovery error bound for low CP rank tensors decays to 0 faster than the 1-bit tensor recovery for any W larger or equals to 2. And the bound for SVD tensors is even smaller. For example, in the 3-order case, the denominator in our result is N, but the denominator in the 1-bit tensor recovery has an 1 over 2. And when reduced to the matrix case, that is W equals 2, both general tensor and SVD tensor show that the quantized matrix recovery has an error bound of square root of R over N, which is the same as the smallest error bound in the matrix case. And here we propose 2 efficient algorithms to solve the non-convex problems. For general tensors, since rank X is smaller or equal to R, there exists a rank R decomposition. Then we change the rank constraint into a penalty function in the objective. And we will add a positive penalty parameter before this penalty function. The equality constraint holds when the penalty parameter goes to infinity. We revise the feasible site to add constraints that quantization boundaries shall not be too close to avoid trivial solutions in practice. The resulting feasible set is shown as equation 13. And we use alternative proximal gradient descent to solve the problem. Step sizes are chosen by calculating the Lipschitz constants of the objective gradients. And our algorithm TAPGD approved to globally converge to a critical point of the non-convex problem from any initial point, as long as the sequence of the variables is bounded. And since the problem for SVD tensor has an extra orthonormal constraint on tensor decomposition components, we apply different updating strategies with orthonormal projections. To demonstrate the effectiveness of our method, we first conduct experiments on synthetic data. And we choose the quantized level case to 2 and 4 respectively. We compare our method to the 1-bit tensor recovery method and the quantized tensor recovery method. And we show that our method outperforms the existing works. And we also observe that when the rank of the tensor increases, the recovery error also increases. When the dimension of the tensor increases, the recovery error decreases. And these results are aligned with the theoretical analysis. We then conduct experiments on recommender system dataset, and we use in-car music reading system dataset. And there are missing data here. We separate the observed data into 2 parts. 80% of the observed data is used to using our method, and 20% of the observed data is used for evaluation. And because we don't know the ground truth rank R, so we choose R within a certain range, and we find that within this certain range, the recovery error are all relatively low. And we also compare with a general non-convex tensor recovery method and show that our method outperforms the general tensor recovery method. And these also support our hypothesis that the real ratings actually lie in the real value domain instead of the concrete value domain. And finally, we conduct experiments on image dataset. And here we consider 2 scenarios. One is that we know the quantization rule, and the other is the quantization rule is unknown. And we show that in both cases, our method outperforms the existing works. And we also compare the time cost to the 1-bit tensor recovery. And we show that our method has can get a good result using less time than the existing work. Thank you for watching.